The question I'd like to talk about in this video is, when does exponentiation commute? Now, just to motivate the question, let's review what we normally mean by the commutative law, or what it means for two objects to commute under some operation. So let's say we had two objects, two real numbers, two rational numbers, whatever, x and y, and let's say we're multiplying the two numbers. Now, if the commutative law holds under this operation, we're allowed to say that x times y is the same thing as y times x. And we're very familiar with this. This typically holds for rational number arithmetic, real number arithmetic. And the question I'd like to ask in this video is it possible to find pairs of numbers, let's say some pairing of numbers x and y, where it's true that x to the y power is equal to y to the x power? That is, under what pairs of numbers is the answer unchanged when you flip-flop the base with the exponent? And now, just to reassure you that this isn't just a question which has no answer, or a question which has boring answers, if we take, let's say, 2 to the 4th power, and we try commuting this 2 to the 4th, is that equal to 4 squared? And you could just do the computation here. You'll see that both sides are equal to 16. So we have found at least one pair of numbers, that is 2 and 4, or you could say 4 and 2, which commute under the operation of exponentiation. And now, if it's not obvious already, this is not in general true. If I take, let's say, 3 and 2, the pairing 3 and 2, and I compute 3 squared and 2 to the 3rd power was 3 squared, that's equal to 9, 2 to the 3rd, that's equal to 8. So this is not true. So we see that this is not in general true of exponentiation, that we can't just flip-flop the base and exponent. But what we're going to tackle in this video, and perhaps another video too, is how to find pairs of numbers, x and y, where you're allowed to flip-flop the base and the exponent. Before we really get going with the math here, let me first point out that besides this nice case where exponentiation commutes with the 2 and 4 pair, we can always take some number and pair it with itself, and that'll commute under exponentiation. And these are sort of the boring cases. For example, let's say we had the number 3, and we raise it to its own power. Now, obviously, when we switch base and exponent are the same thing, so we switch it, it's still the same thing. So the pairing 3, 3, that'll commute under exponentiation, and so will the pair 7, 7, or in general, AA of numbers. But what we're looking for is some pair of numbers, x and y, where x is not equal to y, where it's true that, once again, x to the y is the same thing as y to the x. Now, let's think about some strategies that you might use to find some pairs x, y that commute. Now, we could try to do some algebra on this. Since we have stuff in the exponent, let's try taking the logarithm of both sides. So I have the log of x to the y power is equal to the log of y to the x power. And I use that power rule of logarithms, that y is going to come out front. So I'm going to have y times the logarithm of x. And I use the power rule on the right-hand side, so I get x times log y. And by the way, this log could be base 10, could be base e, could be base 7, could be whatever you would like it to be. And let's take this equation. Let's stick all the x's on one side and all the y's on the other side. So what I'm going to do is I'm going to divide both sides by x. So I'm going to have y log x over x. X is canceled there, so I get log y. And now let me move all the y's onto the other side. So I'm going to divide both sides by y. The y's cancel here. So I get log x divided by x is equal to log y divided by y. Now, this doesn't help us too much, since we don't really have one variable completely in terms of the other variable, But this is a pretty interesting property of these x and y pairs. And what this says is that if some x and y pair is going to commute under exponentiation, the following equation must be true. And if you try out this computation for the case of 2 and 4, so let's try that 2 and 4 case, which we know works. We have log of 2 over 2 is equal to log 4 over 4. And you can compute that, or you can just do some algebra on this to show that these two sides are equal. And you can indeed say that this relation will hold. So that's one relation we've observed that must be true between that x and y pair. Another one, another pretty interesting one, which has to hold as well, is if we go back to this equation here, let me just rewrite it, x to the y is equal to y to the x. Let's say we want to try to, once again, get all the x's on one side, all the y's on the other side. So what I'm going to do first, I'm going to take the left-hand side and the right-hand side, and I'm going to raise, or I'm going to take the 1 over y power of both sides. So I have x to the y to the 1 over y power, and to do the same thing to the right-hand side, I have y to the x to the 1 over y power. So I have x to the y over y power, or just x. That's equal to y to the x over y power. And very similarly, let me take both sides of this equation to the 1 over x power. So I take that right-hand side to the 1 over x power as well. And what I get is x to the 1 over x is equal to, let's see, x cancels with that x there, so I get y to the 1 over y. So we see that this relation between the x and y pair must also be true. And again, if we substitute that known pair 2 and 4, we get 2 to the 1/2 power is equal to 4 to the 1/2 power. And you can just check that computation to see that this is true. Another way of writing this is that the square root of 2 is equal to the 4th root of 4. And this is indeed true. But let me show you where all this is going. Let me go back to that last relation that we found between x and y, that x to the 1 over x power is equal to y to the 1 over y power. Now, one method that you might use in terms of solving equations is just taking a guess. And you could do that. You can do some numerical solutions to this. Or you can try to algebraically solve for them. And in this case, it's not entirely obvious what you do here, how you solve for one symbol in terms of the other, how you solve for y in terms of x, or solve for x in terms of y. Although it can be done, perhaps I'll cover that in the next video. But another strategy that we can use is called parametrization. And what this is going to do is introduce some extra variable, which I'm going to call t, which we use as a guessing variable. We plug in some value of t, and it's going to give us the corresponding values of x and y. And what I'm going to do here is I'm going to take the guess that the substitution y is equal to t times x is going to work. Or let me just try out the substitution now. Y is equal to t times x. Another way of writing this is that t is equal to the ratio y over x. And let me try that out here. Now, what do we get here? Let me substitute for y in terms of tx, and let me leave the x's alone and see if I can solve for x. So what do I get here? I get x to the 1 over x. I'm going to make that substitution for y. I get tx raised to the 1 over tx power. And now, just to clean this up a little, I'm going to take both sides to the x power, just so that those x's in the denominator cancel out. On the left-hand side, I just get just x is equal to tx to the 1 over t power. And now let me distribute that exponent to both terms there, or both factors there. So I get x is equal to t to the 1 over t power times x to the 1 over t power. And now remember, my goal is to solve for one variable in terms of the other. And now what I'm going to do here, I'm going to try to solve for x in terms of t. So I'm going to try to move all the x's onto one side. So what I can do here is I observe this x to the 1 over t here, and I'm going to try to move it onto that side there, to the left. So what I'm going to do is divide both sides by x to the 1 over t power. And on the right-hand side, that cancels. Right-hand side, I get t to the 1 over t. And what do I get for the left-hand side? So I have the same base here, x and x. Remember that x is being raised to the 1 power implicitly. So what do? I subtract the exponents. So I get x to the 1 minus 1 over t. And what is 1 minus 1 over t? Let me just write that out. 1 minus 1 over t. 1 can also be written as t over t. And I have that 1 over t there. I have the common denominator, so I get t minus 1 over t. So I see that the new exponent is going to be x to the t minus 1 over t. And again, that's equal to the right-hand side, which is unchanged. And now for the last trick, I want to solve for x. So I'm going to raise both sides to the reciprocal of this power. So what I'm going to do is, let me just copy what I have down there. X to the t minus 1 over t is equal to t to the 1 over t. I'm going to raise both sides to the t over t minus 1 power. I'll just write that there, t over t minus 1 power. T over t minus 1. Since these are reciprocals, they cancel. So I get x to the first power, or just x, is equal to t. And what's the exponent there? These t's are going to cancel. And so I get 1 over t minus 1 as that new exponent. So that's my first equation there for x. That x is equal to t to the 1 over t minus 1. And now I found x in terms of t. Now, to find y in terms of t, I go back to this equation here, that y is equal to t times x. And I see that just to solve for y here, that all that requires is that I multiply what I found for x by t on the left. So I get y is equal to t times t to the 1 over t minus 1 power. And again, here I have that 1 implicitly. So now I have t to the sum of 1 and 1 over t minus 1. So let me write that out here. 1 plus 1 over t minus 1. 1 can also be written as t minus 1 over t minus 1. Then I have that there, 1 over t minus 1. I combine the numerators. That minus 1 and the 1 are going to cancel. So I get t for the numerator, and that's over t minus 1. So for y, the new exponent becomes t over t minus 1. And these are my two equations for x and y. So what is the strategy here? It's guess or pick some value for t, and then calculate the x and y that's going to arise from that. So here, what we've just done is we've parametrized this equation. Instead of having an equation that has x's and y's only, we've separated it into two equations, here and there, which have x and y by themselves in terms of t. So now let me rewrite those two parametric equations that we have. We saw that x is equal to t to the 1 over t minus 1 power. And secondly, we saw that y is equal to t to the t over t minus 1 power. So what that means is that we can start plugging in values of t. So we're going to plug in some value of t, and that's going to give us an xy pair, which solves the following equation. And I claim that it solves this equation because we just derived it from this equation. But if you wanted to, if you were a little bit masochistic, you could take this expression here, raise it to that power, that would be x to the y power, and then you take this expression here, the y, and raise it to this power, that would be y to the x. And you can verify, just use your exponentiation rules, that these two sides are equal to one another. But the derivation's, in my opinion, easier than that. So now we have these two equations. Well, let's try plugging in some values of t. And in this video, I'd like to consider three values of t, three pretty nice values of t that are going to give us some interesting results. Let me first consider the case where t is equal to 2. So t is equal to 2. That means x is going to be equal to 2 to the 1 over 2 minus 1. 1 over 2 minus 1. And that's equal to 2. And what's that exponent there? 1 over 2 minus 1. That's equal to 1, which is equal to 2. So we see that x is going to be equal to 2 here. And what's the corresponding y value? Again, just plug it in. I get 2 to the 2 over 2 minus 1, which is 1, which is 2 squared, which is 4. So it gives me y is equal to 4. And that tells me that when t is equal to 2, the corresponding xy pair, which will commute under exponentiation, is that pairing 2, 4. And that's no surprise that there is some t corresponding to that pair, which works. We saw that pretty early on. So this is a pretty nice confirmation that our method works, that we plug in this value of 2, and we get some pair which we know commutes under exponentiation. Now let me take another value of t. Let me take the case of t is equal to 3. So again, I plug it into the two parametric equations. I get that x is equal to 3 over 3 to the 1 over 3 minus 1 power. That's equal to 3 to the 1/2 power, which is the same thing as the square root of 3. So that's going to be the x corresponding to that t. And what's the corresponding y? I just plug it in again. I get 3 to the 3 over 3 minus 1, which is 2. So I could keep it like that. Or I can also write it as the square root of 27 as the corresponding y value. And what this implies is that the pair square root of 3, square root of 27 will commute under exponentiation. That is, the square root of 3 raised to the square root of 27 power is the same thing as the square root of 27 raised to the square root of 3 power. So this is pretty interesting, and you can do the calculation here if you want to convince yourself. But we've just shown algebraically that this has to be the case, and that this is another interesting pair of numbers which commutes under exponentiation. So I'll write that in there. Square root of 3 and square root of 27. Those two will commute under exponentiation. And now, let's see if I can think of another interesting t value here. Let's say t is equal to 2/3. A little bit more complicated. So again, we just plug it in. We get x is equal to 2/3 this time. And now let me adopt a little bit more of a convenient notation. Instead of writing the superscript to denote the exponent, let me write the up arrow. And then what follows to the right of the up arrow is going to be the exponent. So plugging in that 2/3, I get 1 over 2/3 minus 1. And that's going to be equal to 2/3 raised to the 1 over minus 1/3, which is equal to 2/3 raised to the, let's see, to the minus 3 power. And I could just convert that to our ordinary notation. 2/3 to the minus 3 power. Now, of course, that negative exponent means that I could just flip this thing here and get rid of the negative. And what's 3 squared? That's 27. And what's 2 to the third? That's 8. So that means x is going to be equal to 27 over 8 for that t value. And now let's calculate the corresponding y value. So again, I plug it in, the 2/3 raised to the 2/3 over 2/3 minus 1, but we saw before that that's equal to minus 1/3. Those 3's are going to cancel, so what I end up getting is 2/3 raised to the minus 2 power, which is equal to, just converting the notation there, 2/3 to the minus 2 power, and I could take the reciprocal. That's equal to 3/2 squared. Then what's 3 squared? That's 9. And then 2 squared is 4. And that's the corresponding y value for that. So we've seen now that the pair 27/8 will commute with 9/4 with respect to exponentiation. And just to reiterate what all this means, that means that 27/8 raised to the 9/4 power is the same thing as 9/4 raised to the 27 over 8 power. And again, you can do the calculation just to confirm this. But here's another interesting pair of numbers which commutes under exponentiation. Let me summarize what we have thus far. So we found that nice parametrization, x is equal to t to the 1 over t minus 1 power, and that y is equal to t to the t over t minus 1 power. And we plugged in a few values for t. We found that t being equal to 2 corresponded to the pairing 2, 4, which will commute. And we plugged in that other value of 2/3, which corresponded to that other pair, 27/8, 9/4, which commutes. And I believe we had the case where t is equal to 3, and we got yet another pair, which was square root of 3, square root of 27. Now, let's make an observation here. We saw that the pairing that we got out of this was an irrational number. And we noticed that the pairing, when we plugged in t is equal to 2/3, gave us a rational number. Now, why is that? Is it because we plugged in a rational number? Well, if you try this out, if you plug in some number like 3/5 for t, you're going to find that what you get out for the x and y pairing is a pair of irrational numbers. So we didn't get a pair of rational numbers because we plugged in a rational number for t. Now, the real reason that we're getting out to a pair of rational numbers is because we plugged in some t value which has the form some number a divided by a plus 1. That is, we plugged in a number such as 2/3. If you plug in 3/4, you'll also find that the result is rational. If you plug in 4/5 or even 10 over 11, you'll also find that the result is a rational number. And now I'd like to conclude this video by proving that as a theorem. And the theorem is going to say, if t is of the form a over a plus 1, where a is some integer, or a is some integer, then x and y are both rational. X and y are both rational numbers. And now the proof of this isn't too difficult. What I'm going to do here is suppose that t has the form a over a plus 1, and I just plug it in first to x. So what I get here is x is equal to a over a plus 1 raised to the 1 over a over a plus 1 minus 1. And now we're going to do a little scratch work here to figure out what this is. A over a plus 1 minus 1. So I have that, a over a plus 1 minus 1, but 1 can be written as a plus 1 over a plus 1. And in the numerator, I get a minus 1 over the denominator, which is a plus 1. I see that the a's cancel out, and what I get is minus 1 over a plus 1. And that's equal to this denominator here. So that means when I flip the thing, because I want 1 over this quantity, that new exponent is going to become the negative of a plus 1. And the base stays the same. All I did here was invert, or take the reciprocal of this number. So now I have that negative exponent there. So if I take the reciprocal of this, I'm allowed to get rid of that negative number. So I get a plus 1 over a raised to the a plus 1 power. And to make this absolutely clear, let me convert this back to our usual notation. So we're going to have a plus 1 to the a plus 1 power. And I have a, denominator, also to the a plus 1 power. And now observe what we have here. Now a is some integer. And that means that a plus 1 is also an integer. So I have some integer here, a plus 1, being raised to an integer power. So I'm guaranteed that the numerator is an integer. A is an integer down here. A plus 1 is also an integer. So in the denominator, I also have an integer. So I'm guaranteed that x is rational. Let me make a quick correction before I move any further. Let me restrict this to a positive integer, or some natural number. Then this theorem is going to hold. And secondly, when I go to prove that y is also rational, there's an easier way to do this as opposed to doing all this calculation all over again. We go back to the parametrization and we recall that y is equal to t times x. Now we know what t is. We suppose that t is a over a plus 1, and we just calculate what x is. So we just make the substitution. T is equal to a over a plus 1, and x, as we observed here, is a plus 1 to the a plus 1 power divided by a to the a plus 1 power. And now what do we have here? We see that this a is going to cancel with one of these a's down here. So instead of a over a to the a plus 1, in the new denominator, we're going to have just a to the a power. That minus 1 is going to go away. And very similarly, with these two here, we have a plus 1 to the first power, and a plus 1 up here. So only one of those a plus 1s is going to disappear. So we get a plus 1 to the a power up there. And this is equal to y. And you can see here, a plus 1 and a are both integers, so we get integers raised to the integer power. So we're guaranteed that both numerator and denominator are integers. So these are both rational numbers. So that's a pretty interesting result. So it guarantees that we calculate that when we go to calculate something that looks like, again, something form a over a plus 1. So if we go to calculate 100 over 101 for t, that the result, the xy pair, had better both be rational numbers. And there's a very similar statement for when t is of the form a plus 1 over 1. For example, it's 4/3 or 7/6 or 11/10, and so on. And the proof is very similar, and I'll just leave you to show that as an exercise. Just to give you a bit of a preview for what I'm going to do in the next video, is I'm going to return to this equation, to the fundamental equation, x to the y is equal to y to the x. And I'm going to attempt to solve for x in terms of y. And I said before that this is not easily done algebraically, and you're going to need some special tools to do this. So this is going to involve something called the Lambert W function. And what we're going to do is find a formula for x in terms of y, where y is going to be expressed as an argument for the Lambert W function. So that'll be for next video, and hopefully you'll join me for that one. Thanks for watching, and feel free to subscribe.